In this module, we'll introduce you to phases, their properties, transition of phases, and change of properties during transition. Let's start with a system that we are all quite familiar with. Let's take a closed container, and in that container we've thrown in water at 30 degrees centigrade and ice at 0 degrees centigrade. Now before we do any thermodynamic analysis, we observe that ice and water, while made of the same molecule, H2O, have very different properties. One is a solid and the other is a liquid. One is hard and rigid, the other flows. Why is that? Properties of different phases, even though they are made of the same molecules, are different because their structure changes. Consider, for example, molecules that are in a solid-like phase where they are arranged in an ordered, closely packed fashion. Close packing means extremely strong intermolecular forces. It means high density. When I have a force down this way, strong intermolecular forces prevent any kind of cracking or fracture. Also, when I have a force in this way, a shear force for example, it prevents these intermolecular forces, prevent flaking of this material. I could go to a different solid phase where they are not closely packed but still arranged in an ordered fashion. The intermolecular forces are still quite strong, though weaker than in the first case. If I have a compressive force or a fracture force, this material is going to fracture. If I have a shear force, this set of molecules will slide out and hence this material will be given to flaking. In a mobile phase, in a liquid-like phase, all of these molecules are moving around. They are not in fixed positions anymore. They have intermolecular forces, but they are significantly smaller than in this case. Thus, the density of this system is smaller than in this system than in this system. This material will be given to compression, and when I attempt to shear, not only will it flake, this system will actually flow. The molecules will actually go along with this force. As I move from liquid to gases, the translational energy becomes higher. These molecules are moving around even faster. In addition, there are more void spaces between these molecules. Thus, any compressive force, pressure, will act to reduce these void forces, and hence this material will be extremely compressible. Thus we see that the molecular structure, the way in which these molecules are arranged, affects the properties of these materials. Let's go back to the same set of molecules. In a closely packed structure, since these interactions are extremely high, but the molecules are not running all over the place, this system will have a high potential energy, but not as high a kinetic energy. In this case, since the molecules are running all over the place, this system will have a high kinetic energy, but the intermolecular forces will be weak. Thus, the internal energy as well as thermal and pressure properties, mechanical properties, all depend on the molecular structure of the material. With this understanding, I go back to my water-ice system. Let's take this open container with ice, a glass with ice, and we place a thermometer in this, and we place this glass at room temperature, let's say on a table. We know that over time the ice will melt. That is, the material will change from solid phase to liquid phase. Let's look at the system more closely as to what's happening to the system. So let's look at the system in terms of energy it absorbs and how the temperature rises. We start with this phase when it is at a low enough temperature, say let's say at minus 10 degrees centigrade. It begins to absorb energy, and as it absorbs energy, its temperature rises. We continue to see this temperature rise. The material still stays in its ice, in its solid-like form. After a certain point, once it gets to a certain temperature, we see that it still continues to take in energy, but the temperature doesn't rise anymore. In addition, we see that this material is gradually transforming from a solid-like state to a liquid state. So the ice is melting. So in this region, we see that the temperature isn't changing, it's taking in heat, and the ice is melting. Once it comes to this state, when all the ice is melted, we see that the temperature begins to rise again. So this is all water state, the same temperature at which it melted. And we see when we add more heat, again this is water, the temperature begins to rise. So this is a liquid phase, and there is a rising temperature as we add heat. It gets to this point, and any more heat given here doesn't cause any rise in temperature. We see a flat line again. There's no rise in temperature even though heat is coming in at that point. We also observe that steam, the water begins to decrease, the amount of liquid water begins to decrease, and we begin to form steam. And at this point, all the water has been converted into steam. In this regime, there is no rise in temperature. Added heat only causes the transition of water into steam. Once all of the water has been converted into steam, any further addition of heat causes more increase in temperature. We notice that these slopes, the rate of increase in temperature for the same amount of heat given in, the slope changes in the solid state, in the liquid state, and in the vapor state. With addition of heat, a material goes through different regimes of changing temperature and changing density. And density is an indicator of the structure of the material. We notice that the slope of each rising section is different. This implies that the same amount of heat results in varying amount of rise in temperature. This is a property of the material. How does the heat affect the internal energy of a system? How is the internal energy related to the state of a system? These are questions of interest. So when I give heat to a material, what happens to that heat? Where does the heat go? On heating ice, its molecules gain energy in the form of vibrational or rotational energy. So that's a molecule, that's the oxygen atom, there are the hydrogen atoms, they are vibrating and rotating. As I begin to give heat, these vibrational and rotational modes get more and more energy. The energy of these modes can be calculated. So right here, as I'm heating it, in the solid state, the energy is increasing here. Now this gain in internal energy is related to increase in temperature, right here. The increase in energy can also result, as I heat it, can also result in the molecules moving away from each other. In solids and liquids, they do not move away from each other too much. As the molecules move a little away from each other with increasing energy, the material is seen to expand. So we've seen, for example, metals expanding with heat. Sometimes doors do not shut properly owing to expansion. So molecules of a solid vibrate around a fixed position. Their internal energy is the sum of their vibrational kinetic energy and their potential energy due to intermolecular interactions. On adding energy, we saw that the vibration and the rotation of these molecules increases, and they begin to vibrate more, and their fixed position become a little less fixed as they begin to gain energy. This increase in energy can also result in the molecules moving away a little bit from each other. This is thermal expansion, and this here is the coefficient of thermal expansion. It is the change in volume, delta V per unit volume V for a small change in temperature at constant pressure. So it's the change in volume per change in temperature for a unit volume V at a constant pressure. Now what happens to the molecules during the solid to liquid transition? At a certain point, we've added enough energy that there's no more energy to be taken in by vibration. The molecule has reached saturation in its vibrational and rotational modes of energy. What happens to energy added after that point? With more added energy, the molecules will transition to a mobile state. So at that point, there is no more energy to be taken in here. Added energy will cause a phase transition. The molecules will transition from the solid-like state to a more mobile state. Hence, during this transition, no rise in temperature is observed till all the molecules have transitioned from this solid state to this mobile state. This new water phase with the mobile state has internal kinetic energy from translational modes as well. There was not too much of translational energy in the solid. There was primarily rotational and vibrational. Now in the mobile phase, there's a significant amount of translational energy as well. This energy required to change ice into water or solid into liquid is called the latent heat of melting. Latent means hidden. We could also have solid to solid transition. Sometimes in a solid, molecules are perhaps ordered in a way where they are very tightly packed. So when we add energy, they transition not to a liquid stage, but there is available a slightly less tightly packed state, and they first transition to that stage. So for example, they could go from this hexagonally closed packed region to perhaps a cubic packed region, where there is more space between these guys. The molecules are still in their fixed position. They can only vibrate, but they have more space to themselves. Since the order has changed, since the molecular arrangement has changed, the properties also change. So depending on the molecular structure, the molecules have different capacity to absorb heat. And this capacity to absorb heat is shown by the slope of this line. The slopes of temperature versus heat are different in different regimes of the phase. The slope is different here, the slope is different here than it is here. And this is different because the nature of constraints in vibrational, rotational, and translational energy are different. So the modes of energy they have in which they can absorb heat or absorb energy are different. Hence, the amount of temperature rise for a certain amount of energy that is given to the system also changes. This is called the heat capacity of the material. Heat capacity, C, is equal to delta H over delta T per mass. We can measure the heat capacity when the system is not changing its phase, when the material is not changing its phase. Let's look at internal energy of liquids. With liquids, in addition to an internal energy that's related to vibration and rotation, they also have a translational kinetic energy. In addition, they have potential energy based on interactions between the molecules. The intermolecular energy is stronger than gas, and it allows the molecules to stay together in the liquid phase right here. The molecules have greater kinetic energy owing to greater translational energy. As heat is added to the system, temperature rises depending on the heat capacity of this range of this liquid. There's also a small but significant expansion of the liquid with rising temperature. Again, this is given by the thermal expansion coefficient at constant pressure. Now as we continue to add heat to this, there's a certain threshold where the internal energy modes are saturated within the liquid state. More energy causes the molecules to move to a state where there's almost no intermolecular interactions, or the intermolecular interactions become extremely low. This implies that the molecules can pretty much go wherever they want to. So with more energy added, they transition from a liquid state to a vapor state. During this transition, there is no rise in temperature, but once they have reached this state, added energy allows or causes a rise in temperature. This energy required for change of water into steam, liquid into vapor, is called the latent heat of vaporization. Once it reaches a vapor state, when the temperature continues to rise, there will also be an expansion in the gas, and there is significant expansion compared to liquid and solid phases. We have seen that adding or removing heat in a system changes the temperature, the pressure, the density of the material, and hence the properties of the material. The internal energy of a system, we said, is the energy required to form the material in that state. When material is less dense, molecules are far apart and not interacting as much, but they have higher translational kinetic energy. When material is more dense, the molecules are closer and have attractive interactions, but much lower translational kinetic energy. The internal energy of water is lower. It requires the latent heat of vaporization to turn it into steam, which has a higher internal energy. Thus, we saw how the structure of matter changes with changing energy, and we saw that the properties go through discontinuous changes when the phase of matter, that its structural order, changes. This understanding, this change in phases, and understanding of how properties of material change is important in designing materials as well as in designing processes. We will keep these in mind when we do further thermodynamic analysis.